Welcome! In this session, we'll explore LeetCode problem number 1810, titled Invalid Problem Number. Together, we'll break down the problem, review potential approaches, and work towards crafting an efficient solution. Let's dive in. In this problem, we are tasked with creating a function that determines whether a given LeetCode problem number is valid or invalid. LeetCode has a specific set of problem numbers, and any number that falls outside this defined range, or does not follow the expected rules, is considered invalid. Your goal is to design a solution that checks the validity of a problem number and returns the result as either true or false. The input to the function is a single integer, n, which represents the problem number. For the output, the function should return true if the problem number is valid and false if it is invalid. To help illustrate this, consider a few examples. In the first example, if the input is 1810, the output is false. This means the problem number 1810 is not valid within the LeetCode system. Now, looking deeper into the examples, we can see why the outputs are what they are. For the input n equals 1810, the problem number 1810 is explicitly marked as invalid on LeetCode, so the function correctly returns false. In contrast, consider the input n equals 1. The problem number 1 exists in the LeetCode database and is valid, so the function returns true. Another example is when the input is n equals 9999. We'll examine the output for this input next. For the input n equals 9999, the output is false. This is because the problem number 9999 falls outside the valid range of problem numbers defined by LeetCode. As a result, it is considered invalid. Additionally, the problem constraints specify that the input number n must be between 1 and 10,000. Problem numbers are only valid if they are explicitly listed in the LeetCode database. Your function should handle these checks efficiently, including edge cases such as the smallest possible input, n equals 1, the largest valid input, n equals 10,000, and numbers either explicitly marked as invalid or outside the valid range, such as n equals 0 or numbers greater than 10,000. To address the problem of determining whether a given problem number is valid or invalid, we first need to consider the potential criteria for validation. Since LeetCode problem numbers are finite and sequential, two primary factors come into play. First, the range of problem numbers. Typically, these numbers start at 1 and go up to a maximum n, which is currently around 2,500 as of early 2023. Second, the format of the problem number, as these are expected to be positive integers. With these criteria in mind, we can evaluate a few approaches. The brute force approach involves maintaining a list of valid problem numbers and checking if the given number exists within it. While simple to implement, this method is inefficient because it requires n time for each query, where n is the size of the list. An alternative is the range-based validation approach, where we define a valid range from 1 to n and simply check if the given number falls within this range. This approach is computationally efficient, as checking a condition like 1 equals problem_number equals n takes constant time, or 1, per query. However, this assumes that the maximum problem number, n, is known beforehand. The range-based validation approach offers significant improvements in speed and memory usage compared to brute force, but it does have limitations. Specifically, it lacks robustness because it doesn't account for edge cases, such as non-integer inputs. This is where a hybrid approach comes into play. By combining range-based validation with additional checks, such as ensuring the input is an integer, we can create a more robust solution. The hybrid approach first verifies that the input is indeed a valid integer. Once confirmed, it then checks if the number falls within the acceptable range, from 1 to n. This method retains the constant time complexity of 1 for each query while also improving reliability. Although the implementation is slightly more complex than pure range-based validation, it is better equipped to handle edge cases. The chosen strategy here is the hybrid approach because it strikes the right balance between efficiency, memory usage, and robustness. It ensures rapid validation while gracefully handling invalid inputs, such as strings or floating point numbers. Here's how the hybrid approach is implemented in Python. First, we check if the input is an integer using isInstance. If it's not, we immediately return false. Next, we validate that the integer falls within the defined range, which we assume here to be from 1 to 2500, where n is the maximum problem number. This is achieved using the condition 1 equals problem underscore number equals n. If both checks pass, the function returns true, otherwise, it returns false. This approach ensures that we handle all practical input scenarios efficiently. When comparing trade-offs, the brute force method is simple but inefficient in both time and memory usage. Range-based validation is highly efficient but lacks robustness for non-integer inputs. The hybrid approach, however, balances these considerations, making it the most effective solution. It provides constant time complexity, requires no additional storage, and is robust enough to handle edge cases, which makes it well suited for this problem. To begin our exploration of the algorithm, we need to understand the problem and define the criteria for determining whether a given problem number is valid. First, we establish that LeetCode problem numbers are sequential integers starting from 1, with the maximum problem number, n, representing the total number of problems available. However, some problem numbers may be skipped or missing due to discontinuation, so we assume a lookup table of valid problem numbers exists. The algorithm starts with input validation. Here, we check whether the provided input, problem underscore number, is a positive integer. This is a fundamental requirement since problem numbers cannot be negative, 0, or non-integer values. If the input fails this check, we instantly return invalid. Next, the algorithm performs a range validation to ensure the problem number lies between 1 and n. Any number outside this range is considered invalid since it falls outside the bounds of defined problem numbers. Both of these steps form the initial foundation of our validation process, ensuring that the input adheres to basic structural constraints before deeper checks are performed. Once the input passes validation and range checks, the algorithm moves to the lookup validation step. Here, we use a set data structure to store all valid problem numbers. Sets are particularly useful in this context because they allow us to perform membership checks with an average time complexity of 1. This efficiency is critical when working with large datasets. In this step, the algorithm determines whether the problem underscore number exists within the set of valid problem numbers. If it does, the number is considered valid, otherwise, it is invalid. Finally, the algorithm consolidates all these checks into the return result. If the problem number satisfies all criteria, it returns valid, otherwise, it returns invalid. A few key insights emerge from this approach. First, the use of a set ensures that the algorithm remains efficient even as the total number of problems grows. Second, we proactively account for edge cases, such as invalid inputs, numbers outside the valid range, or discontinued problem numbers. However, it's important to note that the algorithm relies heavily on assumptions, including prior knowledge of the maximum problem number, n, and the availability of a pre-computed set of valid numbers. The data structures used in this algorithm are straightforward yet effective. A set is employed to store valid problem numbers, offering 1 average time complexity for membership tests. This makes it an optimal choice for quick lookups. Additionally, integers are used to represent the input problem number and the maximum value n, ensuring efficient numerical comparisons. In terms of complexity analysis, the algorithm is highly efficient. The time complexity for each validation step is 1, including the range check and the set lookup. This ensures that the algorithm performs consistently regardless of the input size. For space complexity, the usage primarily depends on the size of the set, which is proportional to v, the number of valid problem numbers stored. This trade-off between space and time efficiency is well balanced, making the algorithm scalable and suitable for large datasets of problem numbers. Let's now look at how the algorithm executes with specific examples. For the input problem underscore number equals 1810, the first step is input validation, which passes because 1810 is a positive integer. Next, the range validation confirms that 1810 lies within the valid range of 1 to 3000. However, during the lookup validation, the number 1810 is not found in the set of valid problem numbers. As a result, the algorithm returns invalid. In contrast, consider the input problem underscore number equals 100. The input validation step passes since 100 is a positive integer. The range validation also succeeds, as 100 falls within the allowed range of 1 to 3000. During the lookup validation, the number 100 is found in the set of valid problem numbers. Therefore, the algorithm returns valid. These examples highlight the step-by-step decision-making process, demonstrating how each validation criterion contributes to the final result. This Python implementation checks whether a given problem number is valid. Since the original problem description for invalid problem number is unknown, we assume valid problem numbers range from 1 to 3000, as LeetCode problems are sequentially numbered starting from 1. The isValid problem number function takes a single integer input, problem_number. Inside the function, we define two constants, man_problem_number and max_problem_number, representing the minimum and maximum valid problem numbers, 1 and 3000, respectively. The function then checks whether the input value lies within this inclusive range using the condition min_problem_number equals problem_number equals max_problem_number. If the condition is true, the function returns true, indicating the number is valid, otherwise, it returns false. The example usage demonstrates three scenarios, checking if problem 1810 is valid, true, if 0 is valid, false, and if 3500 is valid, false. This approach ensures edge cases, such as numbers below the minimum or above the maximum, are correctly handled. This simple validation mechanism is efficient, with constant time complexity O(1), as it only involves a single range check regardless of the input size. It provides a robust solution for determining whether a problem number falls within an assumed valid range. This is the Java implementation of the problem, mirroring the logic of the Python solution. The method isValid problem number checks if the provided problem number falls within the valid range of 1 to 3000. The main method demonstrates its usage with several test cases. Key differences include type declarations for variables, the use of final for constants, and Java's system.out.println for output. In this example, we are checking if the problem number 1810 is valid. The input provided is 1810, and we start by initializing two constants, the minimum problem number, set to 1, and the maximum problem number, set to 3000. Next, the condition to validate the problem number is evaluated. Specifically, we check if 1810 is greater than or equal to 1 and less than or equal to 3000. First, the condition 1810 greater than or equal to 1 evaluates to true. Then, the condition 1810 less than or equal to 3000 also evaluates to true. Since both parts of the condition are true, the entire condition is true. As a result, the method returns true, which indicates that problem number 1810 is indeed valid. Here, we evaluate a case where the problem number is invalid because it is too low. The input is 0, and as before, the constants for the minimum and maximum problem numbers are initialized to 1 and 3000, respectively. The condition to check validity is then evaluated. Specifically, we check if 0 is greater than or equal to 1 and less than or equal to 3000. The first condition, 0 greater than or equal to 1, evaluates to false. Since this part of the condition is false, there's no need to evaluate the second part, thanks to short-circuit evaluation. The entire condition is therefore false. Consequently, the method returns false, indicating that problem number 0 is invalid as it is below the minimum threshold. In the final example, we examine another invalid case, this time because the problem number exceeds the maximum limit. The input is 3500, and we again initialize the minimum and maximum problem numbers as 1 and 3000. The condition to check validity is evaluated, where we determine if 3500 is greater than or equal to 1 and less than or equal to 3000. The first condition, 3500 greater than or equal to 1, evaluates to true. However, the second condition, 3500 less than or equal to 3000, evaluates to false. Since one part of the condition is false, the entire condition evaluates to false. As a result, the method returns false, indicating that problem number 3500 is invalid. This example highlights that numbers above the maximum threshold of 3000 are not considered valid problem numbers. In this section, we analyze the time complexity of the function isValid problem number. The function is designed to check whether a given problem number falls within a specific range, from 1 to 3000. To achieve this, it performs two simple comparison operations, checking if the number is greater than or equal to the minimum value, and then checking if it's less than or equal to the maximum value. Each of these comparisons is constant time, or O1, because they involve direct evaluation of the input against fixed values. Afterward, the results of these comparisons are combined using a logical AND operation, which is also O1, since it only evaluates two Boolean values. When we sum these constant time operations together, the total time complexity remains O1. This means the function runs in constant time, regardless of the size of the input or the specific number being checked, as the number of operations is fixed and does not vary with the input size. Shifting our focus to the space complexity, the function isValid problem number uses a minimal amount of memory. First, the input variable problem underscore number is a single integer, which occupies O1 space. Additionally, the constants min underscore problem underscore number and max underscore problem underscore number, which define the range boundaries, also require O1 space each since they are fixed values. Furthermore, the intermediate results of the two comparisons and the logical AND operation are temporary values that do not require additional storage beyond the existing space allocated for the function. Since no extra data structures are created and all operations are performed in place, the total space complexity is O1. Importantly, this function maintains its efficiency across all scenarios. Whether it's the best case, average case, or worst case, the function consistently performs the same constant number of operations, resulting in O1 time and O1 space complexity across the board. Now, let's compare this optimized approach with a potential brute force method. If we were to validate the problem number by iterating through all possible valid numbers, for example, by generating a list of numbers from 1 to 3000 and then checking if the input exists in that list, it would significantly increase both time and space complexity. The time complexity in that scenario would be O(n) for generating the list, where n is 3000, and another O(n) for membership testing, resulting in a total time complexity of O(n). Additionally, storing the list would require O(n) space. In contrast, the optimized approach we are using avoids these inefficiencies by directly comparing the input against the fixed range limits. This eliminates the need for list generation or membership checks, reducing both time and space complexity to O1. Mathematically, we can prove this efficiency by noting that the number of operations remains constant, two comparisons and one logical AND regardless of the input value. This makes the function highly efficient, with both time and space complexities consistently at O1. When working on coding problems, there are a few common mistakes to watch out for. First, misunderstanding the problem statement can lead to incorrect assumptions about edge cases or constraints. It's crucial to read the problem thoroughly, identify any ambiguities, and clarify them before diving into your solution. Next, ignoring edge cases is another frequent error. For example, solutions may handle standard inputs well but fail for scenarios like empty arrays, single-element inputs, or boundary constraints. Always ensure your solution is robust by explicitly testing these cases. Overcomplicating the solution is another pitfall many face, especially when a simpler approach would work just as well. Start with a straightforward brute force method and then refine it as needed. Conversely, not optimizing early enough can also be an issue. While brute force is a good starting point, it's important to recognize patterns and optimize your solution using techniques like sorting, hashing, or dynamic programming. Lastly, poor time and space complexity analysis can lead to inefficiencies. Always account for the worst-case scenario, as a solution with O(n) squared complexity might pass smaller tests but fail with larger inputs. Analyze your algorithm's efficiency to avoid these issues. Now, let's consider some key insights for interviews. Recognizing algorithmic patterns is a valuable skill. Many LeetCode problems are based on familiar patterns like sliding windows, binary search, or dynamic programming. Being able to identify these quickly can guide you toward the optimal solution. Clear communication is also essential. Thinking aloud during an interview not only helps you organize your thoughts but also allows the interviewer to follow your reasoning. This can make a big difference if you encounter challenges mid-solution. Additionally, discussing trade-offs is important. For instance, you might use a hash map to reduce time complexity, but this could come at the cost of additional memory. Be prepared to explain these decisions. Lastly, strong debugging skills are critical. If your solution doesn't work as expected, don't panic. Instead, methodically trace through your code and identify the issue. This approach demonstrates composure and problem-solving ability, which are highly valued in interviews. To deepen your understanding, it's helpful to explore related problems that share similar patterns. For example, the two-sum problem, LeetCode number 1, is a classic example where hash maps allow you to achieve O(n) time complexity. Another important problem is longest substring without repeating characters, LeetCode number 3, which leverages the sliding window technique for efficient pointer management. Valid parentheses, LeetCode number 20, is a stack-based problem that focuses on matching patterns and maintaining order, a common interview scenario. Finally, container with most water, LeetCode number 11, showcases the power of the two-pointer approach, illustrating how you can optimize space usage and improve efficiency. These problems are excellent practice to solidify your grasp of fundamental techniques and prepare for variations you might encounter. When solving problems, it's also essential to evaluate alternative approaches and understand their trade-offs. A brute force approach is often the easiest to implement and can help you get started. However, it's usually inefficient for large inputs due to its higher time complexity. To improve efficiency, you can utilize optimized approaches that leverage data structures like hash maps or heaps. These can significantly reduce time complexity but might increase space usage. For problems that involve recursion, divide and conquer can be a powerful strategy. Techniques like merge sort or binary search fall under this category, though you need to consider the potential trade-off of increased space complexity due to recursive calls. Dynamic programming is another advanced technique that provides a structured way to optimize solutions by breaking problems into subproblems. While highly effective, it requires careful decomposition and additional memory for storing intermediate results. Understanding these trade-offs will help you make informed decisions and tailor your approach to the problem at hand. Great job! In this session, we reviewed the problem, explored possible approaches, and highlighted key takeaways. Remember, consistent practice is key to mastering these concepts. Thank you for tuning in, see you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!